Let's think a little bit about what the Big Bang Theory suggests, and then based on the theory, what we should be observing today. So the Big Bang starts with all of the mass and space in the universe, an infinitely dense singularity. And a singularity is just something that the math doesn't even apply to it. We don't even know how to understand that. But immediately after the Big Bang, so this occurred 13.7 billion years ago. 13.7 billion years ago. Immediately after it, this little tiny, infinitely small singularity begins to expand. And so for the first 100,000 years, it's still pretty dense. So let me just show this right now. So then it starts to expand. So maybe it gets to this level right over here. And I do not know if the entire universe is infinite or finite, whether it's whether it's a four-dimensional sphere, or whether it goes infinitely in every directions, or whether it's just slightly curved here and there, and maybe flat everywhere else. I won't go into all of that. But then it starts to expand a little bit from the singularity, but it's still extremely dense. It's still extremely dense, so dense that atoms can't even form. So you just have the basic fundamental building blocks of atoms are just all flying around. Electrons and protons, they're just flying around in just this ultra hot, white hot, I could say, or maybe even white hot plasma. So this is, I'll call it white hot plasma. White hot plasma. And then if we fast forward a little bit more, and now this is a point that we think we understand well, but this number, I actually looked at some old physics books, and this number has changed in really the last 15, 20 years, so maybe it'll change more. But after 380,000 years from the beginning of the Big Bang, 300,000 years after the Big Bang, I'll call it the BB. 380,000 years after the Big Bang, and obviously this is give or take a couple of years, the universe expands enough. The universe is now large enough, and obviously I'm not drawing things to scale. The universe is now large enough and sparse enough that it can cool down a little bit. You don't have as much bumping around. It's still a hot place, but now there's it cools down enough that electrons can be captured by protons, and you could actually have the first hydrogen atoms can begin to form. The first hydrogen atoms begin to form. They actually condense. And we estimate this temperature to be around 3,000 Kelvin. So we've cooled to 3,000 Kelvin, but this is still a temperature that you would not want to hang out in. It's still extremely hot. Now, why is this moment important, the first atoms forming? So let's think about what's happening here. You have all of this bumping and interactions. And if because of a bump or some energy release, or because of the heat temperature, if a photon is released, it'll be immediately absorbed by something else. If some energy gets released, it'll immediately be absorbed by something else, because the universe is so dense, especially with charged particles. Here, all of a sudden, it's not that dense. So over here, things that were being emitted could not travel long distances. They would immediately bump into something else. While you go over here, and the universe is starting to look like the universe we recognize. All of a sudden, if one of these really hot, and it's still nowhere near as hot as this universe over here, but if one of these hot atoms emits a photon, and they would because they are at 3,000 Kelvin, if they emit a photon, all of a sudden there's actually space for that photon to travel. So for the first time in the history of the universe, 380,000 years after the Big Bang, you now have photons. You now have electromagnetic radiation. You now have information that can travel over long distances. So given that this happened, it's still roughly 13.7 billion years ago. 380,000 years is not a lot when you talk about 13.7. It still wouldn't even really change the dial, because we're talking in the hundreds of thousands. 0.7 is 700 million years. So this is actually a very small number. So it's still approximately 13.7 billion. It's really 13.7 minus 380,000 years. But given that this was the first time that information could travel, that photons could travel through space without most of them having to bump into something, especially something that's probably charged, the other interesting thing is that these atoms that formed are now neutral. What could we expect to see today? Well, let's think about it. These photons were emitted 13.7 billion years ago. And they were emitted from every point in the universe. So this is every point in the universe. Every point in universe. The universe was a pretty uniform place at that time. Very minor irregularities, but you could see because it was this white hot thing just began to condense, it hadn't formed a lot of the structures that we now associate with the universe. It was just kind of a fairly uniform spread of, at that time, reasonably hot hydrogen atoms. So this is every point in the universe. So let's think about what's going on here. Let me draw another diagram. Let's say that, so we're talking about this point in the universe right over here. The universe is at even 380,000 years after the Big Bang, still much, 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 much smaller than the universe today. But let's say that this is the point in the universe where we happen to be now. At this point in time, there was no Earth, there was no solar system, there was no Milky Way. It was just a bunch of hot hydrogen atoms. Now, if we were at this point in the universe, there must have been points in the universe. There must have been points in the universe at that exact same time, that were emitting this radiation. That were emitting this radiation. And there were actually, every point in the universe was emitting this radiation. The point in the universe where we are now is emitting this radiation. And some of that radiation, so the points that were closer to us, it was emitting that radiation, but it got to us much sooner. It got to us billions of years ago. But there were some points that were far enough that that radiation must be getting to us right now. Or another way to think about it is that radiation has taken 13.7 billion years to reach us. So let me draw. So if I were to draw the visible universe today, and you know from the video about the size, so it's not going to be a scale. It would have to be far, far larger than this circle I drew here. But let's say that this is the visible universe. Let's say that this is the visible universe today. We should be receiving, and we're in the center of it because we can only look the same, roughly the same distance in every direction. We're not the center of the universe. I want to be clear. We're the center of the observable universe because we can only observe the same distance in all directions. Now, we should be, we're receiving some light from 100,000 light years away, and then we're looking 100,000 years in the past. We should be receiving some light maybe 1,000,000 light years that was first emitted 1,000,000 light years before, and that's like looking 1,000,000 years in the past because the light we see was emitted 1,000,000 years ago. I think that's a bit redundant. We could see light that was emitted that's just getting to us after traveling for 1,000,000,000 years. And so we're actually looking at those objects 1,000,000,000 years ago because that's when they emitted the light. So the same way, we can look at objects that emitted their light 13.7 billion years ago, right at the beginning, right at this stage over here, right after 380,000 years after the Big Bang. And so since that light is only just reaching us, we will see it as it was 13.7 billion years ago. So we should see this type of radiation. Now, the other thing to remember, the universe was expanding. When this was emitted, the universe was expanding. The universe was expanding at a very, well, it's all relative, what's a fast rate and all of that, but it was expanding. And we learned on the video in redshift that when the source of the light is moving away from you, or the source of the electromagnetic radiation is moving away from you, the radiation itself gets redshifted. So even though this is at a relatively high frequency, this was kind of, you could almost imagine it was kind of red hot gas. It was at 3,000 Kelvin. Because it was moving away from us, these things, and we learned in the video on the actual size of the observable universe. Even though these electromagnetic waves are taking 13.7 billion years to reach us, in that time, this point in space, the point in space that emitted those electromagnetic waves, are about 46 billion light years away. So that's our best estimate. So this is still stretching away. So theory, if you believe all of this, that this was about 3,000 Kelvin and it gets redshifted, theory would have it that we should see not something analogous to not something analogous to electromagnetic waves being released from a 3,000 degree temperature atom. We should see something redshifted into the radio spectrum. So we should be observing radio waves. And the reason why we're observing radio waves and not something of a higher frequency is because it got redshifted. It got redshifted down into a lower frequency. And remember, we should be seeing it from every point in the universe where the photons have been traveling for 13.7 billion years. we should see it all around us. This is almost a necessity for us to really believe in the current Big Bang theory. And it turns out that we did observe this. And I want to make this is very unintuitive, because you look at any other point in the universe, it's non-uniform. Every other point in the universe, you have stars and galaxies. These aren't atoms anymore. These are stars and galaxies and whatnot. And so there's some points in the universe where you see a lot of radiation, and there's other points in the universe where you see nothing. It's just black. But if this is correct, if this really did happen, we should be able to observe uniform radio waves from every direction around us. And you go 300 or more than 360. We're going in 3 dimensions. Every direction, any direction you point an antenna, a radio antenna, you should be receiving these radio waves that were much higher frequency when they were emitted. They've been redshifted then, but they were emitted 13.7 billion years ago. And it turns out in the late 1960s, they did find these radio waves from every direction. And these are called the cosmic, let me write this down. This is the cosmic microwave background radiation. And it's this in combination. So it's this data that we're getting, this observation, in combination with the fact that the further we look out to galaxies and clusters of galaxies, they all seem to be moving away from us. They're all redshifted, and they get redshifted more and more the further we look out. So this and everything being redshifted away from us are the best 2 points of evidence for the actual Big Bang. So hopefully you found that reasonably interesting.